everybody or whatever before I put the stockpile down here. Okay, so incoming stuff, good. Thank you. Let's see, I have my colored lens. And I wanted to start out with, I always start out with this reminder to myself when I'm writing my notes. I always start out with so far in chapter 15, we've been talking about waves, wave phenomenon. A wave is anything that carries energy in a periodic fashion, a fashion where it repeats itself. We always describe them initially as something y in terms of x and t. So it's actually a two-dimensional quantity, one dimension of space and the dimension of time, and simply as some f of x minus vt. The way we motivate this is to start out by talking about a snapshot of a waveform frozen at time t equals 0, so that this term is gone. Then you describe the waveform, you get a mathematical equation that describes the particular waveform at t equals 0. And then a wave retains its shape and it simply moves as a unit at a velocity v. So this term that we add in later after you allow time to run pulls the waveform back to the initial equation, the f of x. Now that's all rather abstract, so we've got a concrete wave function y equals a cosine kx minus omega t. We even added in there a plus phi naught. This entire thing is the argument. First thing, this negative sign tells you something. What does this negative sign tell you?
Go to the right.
That's, you know what? Not quite correct. Conventionally, moving to the right is in the positive direction. But you really should think that negative sign means it's moving in the positive direction. Nobody says to the right. It has to be positive. It's conventional, but not always. Do watch for something like that. Let's say on a quiz or an exam, where somebody just arbitrarily defines plus as the other direction, and then watches what you do with this negative sign. So the word you use is, the negative sign there tells you that the wave is moving in the positive direction. And of course, if it was moving in the negative direction, you have to put a plus up here. So we put a plus or minus there to indicate whatever the sign here, it's opposite the direction that things move. Furthermore, without looking at your notes, by now do you recall what k is? It's called a wave number, but it's defined in more basic terms. How? 2 pi, yeah, so is it that? 2 pi over lambda. Omega was the angular frequency. Do you remember that's definition? The definition of omega.
2 pi.
It's 2 pi over t. One way of remembering it, of course, is each one of these terms within this argument, of course, has to be unitless. And since x has the units of length, you're probably going to have to divide by something which has to do with length. Or t in time divided by something that has to do with t. I think we also went so far as to say 2 pi times the frequency, 2 pi times the frequency. It's really more conventional to use than nu for frequency. Finally, what was phi naught? What was this one thing here? I'm not going to write an equation for it because we really didn't have it. But can you tell me what phi naught was in words?
Phase shift?
Yeah.
It's the initial phase shift, correct. Most of the time, we're allowed to adjust the axes at will so that we can get rid of this term. Most of the time, phi naught is 0. It's only rarely where you don't have adjustment on the position where you're going to draw the axes where you will find a phi naught. So it's in there just to be complete. All right, so this is called our wave function. That's the wave function. Then we came across the wave equation. I wonder if you could write it down from memory. Once you work with these things, I hope you can write them down from memory. It looks something like this. dy dt. The second time derivative of the function y with respect to time is equal to v squared. There's the wave velocity squared. And then it's the second position derivative, d by dx squared of the same wave function psi, and then, or the same wave function y. Then the very last thing we did, I think, on Monday was to simply test to see if we put this wave function here and here, does the equal sign hold? That is one of the tests you will always need to do if you are given a potential wave function and asked, is this a legitimate wave function? You must test it. You don't just look at it and say, oh, yeah, it looks good to me. Or the teacher gave it to me, so it must be right. Very often I'll give you wave functions, and your task is to test it to see if indeed it is a legitimate wave function. First thing you do is put it in the wave equation and say, does it satisfy the wave equation? All right, so that's the bottom of what I wrote for so far. So this should be reviewed. We talked about it, I think, on Monday, and now I want to pick up from there and continue a little bit further. Any questions about that? All right. The next thing I'd like to talk about is power transmitted in a moving wave. Page 507. Let's see. Why did I reference page 507? There it is. 507. Yeah. We're looking at a diagram that's like this. I took most of the diagram out. I put it on the board here. My sketch is not as good as the one in the book, so you should probably be looking at your textbook, page 507, to look at this. Now, what we're talking about is a waveform that's moving by. It's heading in the plus direction, and I have taken the convention that moving to the right is in the plus direction in this case. So the wave is moving this way, and I'm concentrating on point Q as the wave travels by. So this is a snapshot in time. This is a frozen moment in time. And of course, if the wave is moving that way, Q, following the wave form, will be descending down like that. So the velocity of Q is down. And if we look at the string on the left-hand side of Q, which is what is transmitting the power in the direction of wave movement. If we look at that, there is a force down, which essentially is the tension in the string. So what I'm doing, I'm looking at point Q, and I'm imagining the power that's being provided at Q from the string on the left. And two things that we're interested in is the velocity at Q at this moment and the force being applied, which of course is the tension. Calculate the power as the thing moves in the positive direction. At Q, from the left-hand side, we're able to write down that, well, our author starts with this. Let me start with this. That is that VQ is, there's the J vector, which is, of course, the unit vector in the Y direction, times dy dt, and y, of course, is a function of both x and t. But the first time derivative will give us the velocity. So you have an equation that gives the the description of the wave, you differentiate it once with respect to time, that gives you the velocity, and then he puts the j vector, the unit j vector there, just to give it a direction. Now we're not going to get quite so eloquent with our notation. We're just going to work with power. So power. Remember, we're going to be reusing symbols all the time. Where P, just a week or so ago, was pressure. Now, right today, P is power. And of course, by definition, it's the rate of doing work. That's what power is defined as. So rate of doing work is work divided by the time it takes to do that work. And as you recall, work is what? F dot S. F dot S divided by the time for that to happen. F, of course, is force. S is the displacement vector. When you dot them together, of course, you get a scalar product, don't you? And so we've got to start out with two vectors. We dot them on top and divide by time, the time it takes for that to happen. Now, I'd like to point out two things. First off, let me hear your terminology. If I wanted to say F dot S, of course, your answer is going to be scalar. But can you remember the, what would I say, the algebraic statement? Yes.
Fs cosine theta.
Turn the volume up, please.
Fs cosine theta.
Okay, yeah, that was, she said it correctly. That is F dot S is F S cosine. She said theta correctly, but I'd like you to remember it this way. It's the cosine of the small angle between the two vectors. You remember that, right? If you've got two vectors like this, you could be talking this as theta, or what about that? That could be theta. It's not the angle between the vectors, it is the small angle between the vectors. And of course, that simply chooses the parallel component, doesn't it? But for us, instead of getting so picky about that sort of thing, I'm going to say the following thing. S over t, the distance that you travel divided by the time it takes to travel that distance, of course, is just the velocity in that direction. So, we're going to say that the power is actually going to be F dot V, the power, P, equals F dot V, and of course it's going to be a scalar product. So what you do is you choose the component of F parallel to V, and there is a simple component of F parallel to V, as you can see here. P, power, is going to be F in the y direction, dy dt. But F in the y direction is going to be easy to get also. It's really just a trig function, as you can see. If we define this angle here as theta, then F in the y is going to be just F sine theta. So it's going to be F sine of that angle theta measured with respect to the horizontal, not the angle between the two vectors. I'm also going to put a negative sign there. That negative sign is the vector sense for down. So I'm going to put this over here. I'm going to say down. Even though I know that that's for the negative is down, what I want to do is I want to remind myself that I already put in a negative sign. I put in an algebraic sign to take care of the vector direction. That's just reminding me, oh yes, I already taken care of the fact that it's down. I will forget that later if I don't do that. Well, in this case, whenever you have a waveform moving along a string like this, we're always going to restrict it so that the wave amplitude is kind of small, therefore theta will be small. theta small. And as you recall, that makes it very handy because then sine of theta is approximately tangent theta, which is dy dx. It's the slope. dy dx. Well, that's really nifty because now you see power is going to be simply f and the y times dy dt. So we have t minus t dy dx dy dt. Aha! We now have a statement for power. How lovely. How does that help? Well, for us, let's take a look at this as though it were a cosine function. It sure looks like it must be. For us, y is going to be our old friend, a cosine kx minus omega t. And let's just drop phi naught for now. And when I do dy dx, that, of course, differentiates it once with respect to position, so all it does is pull a k out. There is a negative k, a, sine kx minus omega t. You get the same thing back again in the argument, but where did this negative sign come from? The fact that you're going from cosine to sine, that derivative gives you a negative sign. Now, if we do, oops, it comes from this negative sign here. Excuse me. If you differentiate with respect to time, dy dt, what are you going to get? Well, look, you get a minus omega out front, and then you get the sign back again. So again, the same reason for the first sign, minus omega a sine of kx minus omega t, like that. So it's just wonderful because now power turns out to be a very simple relationship. Power is simply minus t times dy dx, which is the first one, minus, what is it, k a sine kx minus omega t, times dy dt, which is the second one, which is, if you will, minus times minus omega a sine of the same thing, kx minus omega t. And I got to close one more parenthesis, don't I? So what do we end up with? We end up with four negative signs. 1, 2, 3, 4. 4 negative signs. So t k omega a squared sine squared of kx minus omega t. Lovely. What does that mean? That means, first it means we have an expression for power, and that's shown to you on the bottom of page 507. I seem to be missing a negative sign, huh? No, it's correct. It's correct. But I would like to call to your attention a very interesting argument that the author makes following equation 15.11. Figure 15.11, then he begins to talk about the power transmitted, and he argues 1, 2, 3, it looks like 5 points. He argues 5 points, and he ends up on the next page, equation 1512. Equation 1512 is the average power transmitted over a period of time, and this equation is the instantaneous power. So, two things. Remember the difference between the two. This is the instantaneous power at any moment in time, and the equation for average power is given in the book. And look over his arguments, in particular, where did the sign term go? I think his explanation is straightforward. However, if you wish to ask questions about it, do so next time we have a class meeting. What am I doing here? Fact is, I went back and said, well, what if we were going any other direction? What if we were going any other direction and this were a plus? Then this would be a plus here, and this would be a minus or plus. So if I choose the plus sign, in other words, if the wave was moving in the negative direction, I choose the plus sign here, I must choose the minus sign out front. If I choose the minus sign for the wave moving in the proper direction, then I would choose the plus sign out front. That's all I did on the next page. So I just corrected it for the more general case. All right, I want to set up the wave machine now and talk a little bit about how these things happen in particular, so I'll clean up these. Give me just a second, because I want to put the wave machine right here.
Mr. Doran, I've got T and there is tension, right?
Tension, correct. That tension is the force, yes. I don't know about you, but you might want to move for a few minutes just to watch the wave machine.
Big piece tension or big piece period?
Say again?
Big piece tension or big piece period?
No, T is the tension in this case. Otherwise, T can be period, capital T can be period. You're absolutely right. Okay, I want to talk with you a little bit about the wave machine because I want you to see what's going on. For a couple of minutes, if you guys want to come around here to watch it, and I hope you guys can see it adequately. You can move any place in the room you want to move to watch this thing, because it's really important, I think, to see what's going on before you just solve the equation. So this is a really neat thing. I just call it the fishbone, because that kind of tells you what's going on. If you look at it, what it is there's a very thin spring steel spine running down this device. And these more massive rods are soldered onto the spring steel. And the whole idea is you can set up a waveform, and this, because of the inertia of the massive rods, slows down the waveform. So if I want to make a wave that travels slow enough to see what's going on, most wave systems, the wave travels so quickly you can't watch it. So this is just designed to slow it down. Please try to pretend like it's a friction-free device. It's just resting on some little wire things here so that there is a lot of friction in it. But we're going to imagine what's going on with a friction-free device. So I want to talk to you about waveforms when we travel down like that. And sure enough, when it gets to the end of the device, the energy in the wave has got to go somewhere. It can't keep going. There's no more wave system down there, so it reflects back again. That's the first thing I want to call to your attention, and that is that these waves reflect. Now watch, I'm going to put a positive pulse in there. It goes down there like that and reflects and comes back. Well, you can kind of imagine that it looks the same on the way back. I know that its amplitude is diminishing after reflection. And when waves strike a boundary, something always happens. In this case, it struck what I call a soft boundary, as opposed to a hard boundary. A hard boundary is where the wave itself cannot disrupt the medium. In other words, you send a pulse down like that, and instead of having the end free, it's fixed. You know, a little bit like that guitar string we were talking about in the past. You got a guitar string, you pluck the guitar string, the waveform moves down until it hits that bridge where the string itself cannot move. That's a hard boundary. To simulate that, maybe I could get you to volunteer again like you did at the lab, and he's going to be the hard boundary by simply holding that last end one like that. And I'd like you to notice the difference. I'm going to do the same thing. I'm going to send down a positive wave pulse like that. It's going to strike a hard boundary. Can you see? It flipped over, didn't it? As opposed to release it for just a second. We're going to do both of them. That positive pulse comes back as a positive pulse. Now grab it again. Positive pulse comes back as a negative pulse. Thank you. So Yes, give him a round of applause. He did a great job. Didn't he? He did a great job of being a hard boundary. He is our hard boundary. And the reason we want to talk about that is because I want to talk about sending waves down there, having the waves reflect back and superimpose on each other. There'll be a string of waves going that way. They will reflect and come back this way and superimpose. So our next topic is called the principle of superposition, where waves superimpose. And the nice thing is, it's just an algebraic sum. If you try to put two waves in the same place at the same time, they simply add together algebraically. That's all it is. So it's quite simple, a lot of fun, and it does represent a lot of very interesting topics. Now let me just check my notes before I start writing things on the board here. So it says, show the wave machine, show reflected waves, hard reflection, you get a shift of the wave. You know what, I want to do it one more time. You were such a good hard boundary, please come back. What I want to do this time, checking my notes, what I'd like to do this time is to try to make what looks like at least one complete sine wave. It'll strike the boundary, and it should flip, so the positive becomes negative and the negative part becomes positive. You should see it flip over. My argument is going to be that when a sine wave strikes a hard boundary, the entire wave shifts half a wavelength. And so let's see if I can do it. I'm going to send it down like that. It goes down. That's pretty hard to tell, isn't it? It's pretty hard to tell. Let me try it one more time. Just one pulse like that. I think it was a little more obvious with one pulse. I don't know about for you, but when I had two positives and one negative, it came back as one positive and two negatives. Let me try that just one more time. I'll go twice, 1, 2, 2 positive pulses, and it comes back as 2 negative pulses. Okay, good enough, thank you. I promise not to disturb you again unless I reach. All right, so the point is, when a waveform like this strikes a hard boundary, you get a phase shift of half a wavelength. Things flip over. A phase shift of pi radians. Let's see, do I need, no, I don't need this stuff anymore, so I can start erasing. And so I want to describe two different waves, the incident wave and the reflected wave. So, the incident wave, the wave coming into our system, is going to look like this. Y1 is going to be a cosine of kx minus omega t. So here's a wave of known wavelength and of course known frequency. It's moving in what is considered to be the positive direction, and it strikes a hard boundary. Ignoring friction, all that does is phase shift it and reverse its direction. Hence, therefore, Y2, the second wave, is going to be essentially the same thing, a cosine. It's going to have the same wavelength, so it'll have the same k. It's moving in the opposite direction so that it gets a plus sign here, but the same frequency, so omega t. But it also experiences a phase shift phi. And for us, we just argued that phi is pi. It phase shifts half a wavelength or half of a complete cycle, which is pi radians. Now what we're going to do is we're going to look to see what should it look like. Y total is going to be Y1 plus Y2. We're simply going to add the two waves together algebraically and see what happens.
What is this an example of?
Say again?
What is this an example of?
What is the name of it?
What is this an example of?
Oh, what is this an example of? Actually, I think this is the best example of something like a plucked guitar string. Supposed to ends. Pluck it in the middle. Funny he asked that because right there, this is a guitar string plucked in the middle. Both ends are fixed. Interesting. All right. So, here we go. We have, look at this interesting result. We have that, y equals, now see if you can argue this, it's a cosine minus omega t minus a cosine of kx plus omega t. How did a plus sign turn into a negative sign on the second term?
Direction.
Because we have phase shifted halfway, that's why. Half of a cosine, you know, if this is a cosine line, and a cosine looks like this, and this is pi radians. So you have gone from +1 to -1 in a phase shift of a half a wavelength.
Is that supposed to be y total? Y total equals A?
Y total, yes. Thank you. So that's the Y total, and I argue that it would be a negative sign simply by applying this pi shift, that phase shift, turns everything into a negative. Beautiful. It's beautiful because when you look back in your appendices, I never remember this one, cos alpha minus cos beta is equal to 2 times sine the sum, 2 sine alpha plus beta over 2 times the sign of the difference, sine beta minus alpha over 2. So what was a difference between 2 cosine terms turns into a product of 2 sine terms, and of course our alpha is this argument with the negative sign, and our beta is essentially the same argument except this positive sign. That's all there is to it. So for us then, y total is going to be 2. Oh, and we can factor the a out, so it's going to be 2a times the sine of half the sum, alpha kx minus omega t plus beta, which is kx plus omega t over 2 times the sine of half the difference, beta, was kx plus omega t minus kx minus omega t over 2. And of course, immediately you recognize that omega t and minus omega t are gone, and we have 2kx over 2, so it becomes 2a sine kx. And then over here, we have a plus kx and a minus kx. We have a plus omega t and a plus omega t. The kx's are gone like that, and we have 2 omega t over 2, so it's sine omega t. So now we have a very interesting result because we've got, well, twice the amplitude. We'll talk about that in just a moment. And then we've got a term that says sine kx. There is a fixed wave. That wave is fixed in space. It doesn't change. Then there's a sign that says sine omega t. Omega t is something that changes with time only. What I like to do is I like to associate these two. Let me use the blue color. I like to associate this and this. So to write it as 2a sine omega t times the sine of kx suggests that what we end up with then is a sine wave. Let's first look at this sine wave here. Y and x. we have a sine wave whose amplitude is actually governed by 2a times the sine omega t. Which means this whole amplitude term is changing in space like this. The amplitude term, let me put these things down. This amplitude term here can go as high as plus or minus 2a when sine equals 1, or negative 1. The amplitude can be as high as 2a, twice the amplitude of either individual wave, or it decays down to where there's times when sine omega t is 0, so the amplitude of the system is going to be 0. So what you have is you have a stationary wave with two limits of modulated amplitude like this. And the sine wave just sits there and it grows to a maximum of 2a or decays to 0. So what this claims is you're going to have a stationary wave, a wave that doesn't move, and it's going to be, its amplitude is the only thing that's going to change. Its amplitude will be modulated. Well, I guess I lied to you. I'm going to need you one more time. I'd like you to be my fixed barrier one more time. And imagine now that I'm plucking the guitar string somewhere near the middle. And it's going to send a wave down, strike his barrier, come back, and I'm going to keep plucking the string to indicate that it just keeps getting energy pumped in. And we should be able to establish a standing wave. Let me see if I can do that now. It's going down, it's reflecting, and now you can see it. The waveform isn't moving, it isn't going anywhere. The waveform is remaining pretty stationary. It's just that the amplitude is modulated. Thanks again. So this is what happens when you superimpose two waves. They are essentially identical waves. The only difference is the direction that they move. They have the same amplitude, wavelength, so of course they have the same period. They're moving in opposite directions, and you can establish then a stationary wave with modulated amplitude. So I look at this term right here as modulated amplitude, this part right here. The 2a sine omega t is the limits on the amplitude. Sine kx is the actual wave that you get. And since it was a hard boundary, the wave came out looking exactly like it's supposed to. I'll explain that in just a second. Let me make sure I've done everything well here. Sine 2a, okay, good. Wherever sine kx equals 0, remember at his point down there, he was at a 0 point. He was at a point where the system wasn't allowed to move. That's called a node. That's a position of little or no movement. That's a node. So the point that he was holding is a node. We don't have to have it. If I set up a stationary wave like this, you'll notice that there are certain points that never move, and other points that do move. And it doesn't necessarily have to be the ends. It's only when you have a hard boundary do you get a node at the end. In between, where there's maximum movement, it's called an antinode. So new terminology, where there's little or no movement, it's a node. Where there's maximum movement, it's called an antinode. Okay, called nodes. This is where do you get a node? You get a node in our diagram here when sine kx equals 0. Okay, so node. Where do you get a node? It's where sine kx equals 0. Of course, that means where kx is equal to, sine wave is 0 every pi, huh? There's pi, there's 2 pi, 3 pi. So kx equals m pi, And can m equal 0? Yes. M can equal 0, m can equal 1 for 1 pi, 2 for 2 pi's, m can be 3 for 3 pi. So m can be So sine kx equals 0, that's a node, antinode, is when sine kx equals what? Plus or minus 1. And that, of course, is when kx is equal to odd half wavelengths. Pi over 2 or 3 pi over 2 or 5 pi over 2, etc. So, to get that, of course, the mathematicians love to do it this way: 2m plus 1 times pi. And once again, m can equal 0, because when m equals 0, you get half pi. You get 1 on top and you get half pi. So m is allowed to be 0, 1, 2, and so on, like that. Okay. Well, both ends of the string are fixed. They must be nodes. Now for us, we're thinking about a guitar string, so we're thinking about a situation where both ends are fixed. Both ends are like his end, and yes?
Is that having a 2 on there, is that correct? Because wouldn't it make it just pi
Having a 2 where?
on it? M?
That last thing I wrote?
Yeah.
I want it to be odd numbers, right? So if I put in a 0, that's 1/2 pi. If I put in a 1, that is 2 plus 1, that's 3 halves pi, and so on. So it works. Now, what I was about to say was we're imagining that we have something like a guitar string. So the point where I was pumping energy in is the middle of the guitar string. He had one end fixed, the other end would be fixed down here an equal distance away. So we have both ends fixed. You were only looking at half of the guitar string. It's like I plucked it in the middle. Hence, therefore, we do argue, since this is a guitar string, that, of course, when x equals 0, sine is 0, huh? When x equals 0, sine is 0. But we also have to insist then that sine of KL also be 0, where L represents the overall length of the string. There has to be a node at each end. So you have to have a 0 at the far end like that. Well, what does that mean? That means that KL must equal now n pi, because it's a different number. And n can be simply 1. Can it be 0? No, it cannot be 0. Or you have no way. You are now not at x equals 0, so you can't have a 0 when you're talking about this position. So n must start at 1 and continue. So k equals before I wrote that, I wrote this. So I have that, okay. K equals 2 pi over lambda, so I can insert that right here, and I get 2 pi over lambda L equals n pi. And of course the pi's go away, so we end up with lambda, the allowed lambda. I'm going to put this up there and bring this down there, is going to be 2L over n is equal to 2L over n. Those are the allowed values where n can equal 1, 2, and so on. So since there are only certain allowed values, I'm going to subscript this, lambda sub n, meaning that there is theoretically an infinite number of wavelengths that would fit on the string but not any arbitrary wavelength, any wavelength that fits into this group right here. So you can choose any n you want from the list. Notice once again, we have restricted. You can't use n equals 0, or you have no way. But theoretically, you can have an infinite number, an entire ensemble of solutions, but not an arbitrary solution. It's not allowed. Only certain wavelengths allowed. Draw the picture, it says. My notes tell me to draw the picture, so let's draw the picture. In other words, to have two superimposed waves, imagine this represents x equals 0, and this represents x equals L, like this. And of course, using green to represent the string, the only thing that's really required when I draw the picture is that there be a node at each end. I want to draw a picture of allowed wavelengths, the allowed waves that are allowed to be standing waves on this system. The only thing that really counts is that each end be a node, that's all. So I really could, in this case, let's draw this as the first case. And if you think I'm thinking n equals 1, in this case, my standing wave would look like this. That,
Can you use the dark color?
okay, I'll no longer be consistent with the textbook. I'll use blue, or use green. Is that better?
Yes, thank you.
So there's the waveform, and we have satisfied the requirements. There are two requirements. Requirement number 1 is that there is a node at each end. Requirement number 2 is there's at least one antinode, or you don't have a wave. So there's an antinode in the middle and 2 nodes at each end. And in this case, of course, you have the wavelength. That would be lambda sub 1, wouldn't it? Lambda sub 1 is going to be 2L over 1, 2L. So this wavelength is twice the length of the string? Yes, because there's just half of the wave, and then the other half of the wave that should be drawn there is flipped around because it struck the boundary and came back like that. So, you can have a wave whose length is twice the length of the string. Now, the next situation that would work, imagine this. Node at each end, at least one antinode, but we could draw this, couldn't we? So there's a second standing wave where n equals 2. And in this case, of course, lambda sub 2 is going to be 2L over 2, which is L. I'm claiming that the wavelength is the length of the string. Yes, it is, because either one of these, this is one sine wave here. Or this is one sine wave moving in the backwards direction. So you do have it. And we can continue. I'll put one more in. And if I'm going to do that, of course I've got to have 1, 2, 3, like this. There is the situation for n equals 3. And of course, lambda sub 3 is 2L over 3, 2/3 of the length of the string. Yes, 2/3 of the length of the string is one complete wavelength. And so on. And so on. It goes on forever. At least as far as allowed mathematical solutions. Nodes and antinodes, when you have two ends of the string fixed, then the situation looks like the picture I have on the board. Why do we get high amplitudes on the string anyway? You know what I put down here? It's a bit like a swing or the Tacoma Narrows Bridge. Did you watch that film in Physics 4, Tacoma Narrows Bridge? Okay, if you, a couple of you said no, most of you said yes. If you haven't seen it, I'm sure it's on the internet, right? Tacoma Narrows Bridge. That was an engineering disaster, wasn't it? That's where a bridge, a suspension bridge like the Golden Gates type bridge, suspended over a waterway called the Tacoma Narrows in the state of Seattle, not the state of Seattle, the state of Washington, south of Seattle, was subjected to not just a wind, but a wind that was coming in pulses. And slowly but surely there started to be a vibrational mode in the bridge, which over time, it took about 2.5 hours, over time the amplitude got larger and larger and went beyond the design limits of the bridge and destroyed the bridge. That's an interesting video, but I think it's a simpler example to think about a child on a swing. I hope we've all been on a swing before. You know that you don't have to push on a child very hard to start them swinging. And if every time they come back to the stationary position, you give them just a little bit more energy, the amplitude of the swing will get larger and larger. So all you have to do is pump energy in at the same frequency that the system oscillates naturally. And then each time you put energy in, the amplitude increases. On a string, on a guitar string, you pluck the string, you put energy in, and it vibrates in a similar fashion. If you kept putting energy in, the vibration would get larger and larger. A little bit like our example that I talked about, this each time a new pulse of energy arrives, the system is in a phase to accept that energy in a constructive way, much like our experiment. Our experiment for this week was a hollow tube with a tuning fork out front. Let me just draw that, even though I know you know exactly what it looks like. We had a situation where a hollow tube, a piston at some position, a tuning fork, and we were listening for high amplitude sound. What was going on was when you find the correct position for the piston, then you can establish in here a standing wave. Now in this case we have a standing wave where there's a fixed boundary here, so there's a node here, but there's a soft boundary here, an anti-node here. And if you have the correct length, if you have a standing wave in there, then every time the tuning fork puts energy into this column of air, it goes in a constructive way, making the amplitude of the sound wave go up and up and up. So you sought the position to establish a standing wave. The only difference between the pictures we've been showing and this is we have cut it off at an antinode, and the other end is a node. So we have a picture like that. There's the open end, there's the closed end, and we're pumping energy in at a known frequency. So we found the resonance length to give us constructive interference. But the question is, did it look like this, or did it look like this? Look, it could have been, or it could have been, I could put more, and all I know for sure is a node at the piston and an antinode at the opening, and I don't know if it's 1 1/4 wavelengths or 2 1/4 wavelengths or what. I don't know. All I know is I've reached resonance here. That's why you continue to move. You found another position, the next position I will call it, for resonance, which is when the piston is here. And so to go from one picture to the next, to go from this picture to that picture, you must have simply moved by a half a wavelength. It's gotten a half a wavelength longer. So you don't know how many nodes and antinodes there are here. All you know for sure is that there's one more here. You've gone from one antinode to the next. So you don't know here, but when you've done this, you've measured half a wavelength. And of course, according to good, what I call it, laboratory procedures, you keep checking, you go as far as you can. So that is a picture of what's going on, and I think, page 530. They have a much, much cleaner, nicer picture on page 530. So if you haven't already done so, looking in your textbook, sort of models your experiment, the bottom of page 530. Here we're talking about a pipe. This is an organ pipe, a standing wave and a pipe. And there's two different ways they plot them. As we were arguing on Monday, that you can always plot the longitudinal wave as a transverse wave. And for us, I like to think in practical terms, and that is the displacement plot. You see the plot that's on the right-hand side there. That is actually plotting how much the air molecules move, so that at the fixed end, the air molecules can't move. They can't move in and out at the fixed end. So that becomes the node. And at the open end, where the tuning fork is vibrating, the molecules have to move maximum amount. So the pictures that you see on the right-hand side model the experiment in a very practical air movement way. And leads us to the conclusion that the difference between two adjacent high amplitude positions is half a wavelength. Now that you've measured half a wavelength, it's easy to get the speed of sound, because we're accepting the frequency stated on the tuning fork as accurate, and then you measure the wavelength, you've got the speed of sound. So that's kind of a relationship between what we were doing in the laboratory and what we were doing here today in class. Any questions? Because I want to change the subject, but not until I'm sure you're satisfied with what's going on with the lab. How much time? Oh, we got plenty of time for this.
I have a question.
Yes.
On your car string, talking about how all these waves can exist on a guitar string, is it, we're assuming that all waves exist at once?
No. We're gonna, if we're doing a Fourier series, if we had some exotic looking shape to the string, not just a nice sine wave, then the answer would be mostly, not yes, but mostly. But in our case, we're always going to restrict to just some fundamental frequency. We're always going to talk about just one particular wave existing at any given time. When I'm given a solution like I did over there, I'm saying these are all the possible ways of it. And then we select one that happens to be suiting our experiment, our particular experiment. So it's not all of them at once. All of them are allowed. Which one is happening now? Okay? Good question. Anything else? I'm going to move the old fishbone out of the way here, because I want to set up something else in just a minute. But before I set up something else, a good example, I just saw it recently, is the entrance to Long Beach Harbor. At Long Beach Harbor, their breakwater is a very, very long, straight breakwater with just an entrance pupil where the shipping can go in and out. The idea here, of course, is that ocean waves contain a lot of energy. And if that energy is allowed to get into the docking area where the ships are moored, it will do damage to the ships and to the docks and so on. And so you want to stop that wave energy. Now, looking at the wave crests, let's draw them in blue, because water is supposed to be blue, right? Here are the wave crests. Pretty high amplitude waves moving towards the shore like this, with a wavelength can be as much as 40 feet. An amplitude can be 10 feet high. Lots of energy in those waves. The idea is the waves strike the barrier, big splash, most of the energy turns into a beautiful splash, and only a little bit of wave gets through. See, here's one wave that just that little tiny bit makes it through the entrance pupil. Now, very little energy is getting into the harbor. I asked you this question because you know the answer to this. Once that wave goes through the entrance pupil, maybe this is the entrance pupil like this. The wave comes, big splash, and then it makes it through like that. Does it remain this square, clipped off piece of wave and continue to move just like that? What? Of course. What happens to the wave? It doesn't stay a squared off thing like that, does it? What happens to it? It spreads, doesn't it? So the very next wave is going to be doing this. This is called diffraction. Here's a diffracted wave. So a small amount of energy concentrated begins to spread out like that. And the energy density then goes down to just about nothing. It's almost a mile down here to where the ships are moored. By the time these waves get down there, they are inconsequential. To Thomas Young, the idea is this spreading is unique to waves. Waves, when they go through an entrance pupil like that, they spread, they diffract like this. He says, that's the experiment I'm going to do. I'm going to see if light diffracts. If light diffracts, then you can only interpret it as a wave. Or if you do the experiment and it doesn't diffract, then you can say it's not a wave, it must be a particle. So this is a very simple experiment. I really don't understand why it took over 100 years before somebody thought to do this experiment. Now, Young's way of doing the experiment was really interesting. He said, well, let's assume that for a moment that light is a wave. What's going to be the difference in colors? Wavelength. To do this sort of experiment, you're going to have to isolate one color so that you're dealing only with one wavelength. And then he decided to use two, not one, but two entrance pupils. Why? Because you can't actually see the wave traveling like this. You can't see the wave traveling, but what you could see would be the interference of two waves. If light is a wave, then the next set of light waves should look like this. And as they travel further and further, then pretty soon you're going to have interference patterns. You see right here, you have the superposition of two waves. You have a wave crest from this entrance pupil, meeting the wave crest from that entrance pupil. We have two wave crests in the same place. That would mean doubly high amplitude, wouldn't it? And furthermore, if you look in this area, let me use a different color. I shouldn't use a different color because you don't want to get things confused. If I look right here, you'll notice that I have the crest of one wave meeting the trough of another wave. And what happens there? In superposition, what happens? If you've got a wave crest meeting a wave trough, what's going to happen? They cancel each other, right? So what you should get is bright spots and dark spots. You can't see the wave traveling, but when light arrives at a screen, you can see bright and dark spots. So Young's very simple experiment was to look for diffraction. Send monochromatic light, single-colored light, into a double-slit system, and then look and see if you get bright and dark spots. If you do, that's a wave property. If you don't, it's missing the wave property, it's a particle. A very simple experiment. Even simpler for us because we have lasers. Lasers produce nice, bright, single-colored light. Thomas Young didn't have a laser. He had to produce a single color by a different process. But he was able to do the experiment quite successfully, and sure enough, at the far end of the experiment, he got a series of bright spots and dark spots. The only choice you have is to say waves created this pattern. So in 1803, Thomas Young verified the wave characteristic in light with a very, very simple experiment, which you and I are going to duplicate pretty soon. We've got two new experiments to come up. One is with a prism and the other is with a double slit system. And we're going to verify the wave characteristic in light and actually measure the diffraction angles of the various colors of light. So I wanted to today introduce those two topics. Let me just check my notes. I think I've completed everything I wanted to discuss today. Nope, there's one last topic, and I think we don't have time. Young's experiment, and then this topic. So I'll pick this up next time we get together. It's going to take about 20 minutes to talk over that topic. Speaking of the next time we get together, when is the next time we see each other? A week from today, huh?
Oh, you're right, yeah.
You guys have been just working so hard, I've decided to give you Monday and Friday off. Yeah?
So does the Western have lab Friday?
We'll come up with some other arrangement. And by the way, next week, The next two labs are going to require that we sort of do a preliminary briefing together as a group, because some of the equipment is probably unfamiliar to you, and then the biggest thing is